Okay, hi, good morning everyone. I'm Zheng, and I'll be presenting on our paper entitled Efficient Decrease and Conquer Linearizability Monitoring. So, what is linearizability? So linearizability is something that is introduced by Zheng and Wink in the 1990s, and ever since it has become the de facto correctness condition, the standard for deciding the correctness of concurrent objects. And the idea is that in a multi-threaded environment, the time window for which operations executes can overlap with some other operations from the other thread. And the idea of linearizability is that you can pick a specific time within this time window for each of these operations, whereby this operation, you say that this operation automatically executed in that time. And when you order the execution, and it still satisfies the specification of the object. So, for example, on the left, you can see a bad execution because clearly NQ2 came before NQ1 in the queue, but the Q1 came before the Q2. But on the right, it's a good execution because you can schedule NQ2 over here and the Q2 over here, then NQ1 over here and the Q1 over here. Yeah. But unfortunately, verifying whether implementations of arbitrary abstract data type, whether it's linearizable, this is undecidable. So we take a step back and take a pragmatic approach and ask a different question. So given an execution or history of a program, is it linearizable? So the answer has been answered in 1997, actually, that in general is NP-hard. And in fact, Gibbons showed that for the simplest data structures, such as read-write registers, that supports only read and write operations, even for that is NP-hard. And the next natural question to ask is whether there exists tractable variants of the problem. And actually, in the same paper, they also answer this as well. And there is a tractable variant of the problem. And they introduced this thing called the ambiguity restriction, which says that in this history, each value can only be written once. And under this restriction, the problem becomes tractable. And then the next question to ask is whether the same can be applied to other data structures as well. And throughout the years, there have been multiple studies to try to generalize this to other data structures. In particular, in 2018, there's this study to categorize data structures into this thing called collection types, which includes stacks, queues, stacks, queues, and other commonly used data types. But unfortunately, there is a bug. A reduction is unsound, so that this problem becomes open again. So separately, there have been other studies that did not generalize, but study for individual data types under unambiguity restriction, is this problem still tractable? And actually, Gibbons, not long after his first paper, actually he published another paper and says that for stack, queue, and priority queue, this problem is still tractable under the unambiguity restriction. And actually, earlier this year, unbeknownst to us, earlier this year in PLDI, there's another paper that is published, which improved on the complexity on stack to n square, and also give an algorithm for set that runs in linear time. So the problem with existing algorithms is, first, they do not handle picks. Picks are generally read-only operations on these data types. For example, for stack, you can see what's the element on top of the stack without actually popping it, and for queue as well. And another problem they don't handle is empty operations. So empty operations is intuitively operation that has failed. So in real-life programs, when you have concurrent objects, for example, you might want to try pop, and if that stack is empty, then the try pop will return as false, for example. So our paper introduced a few algorithms, and in particular, it improves the stack's time complexity to n log n, and as well as it can be generalized to handle peaks and field operations as well. So beyond that, our main contribution is to introduce this general framework, which is called decrease and concur framework for this problem. And this idea is centered around this thing called linearizability-preserving values, which I will introduce you in a moment. Yeah, so this is the algorithm for solving linearizability problem, given the unambiguity restriction. It's simple, it's 6 lines only, but I have not actually told you what this function actually does. So as the name suggests, this function gets the linearizability-preserving value of the given history H. So you might ask, okay, what is linearizability-preserving value? So a linearizability-preserving value preserves linearizability. Yeah, so given a history, if you have a linearizability-preserving value, you removed all the operations on that value, the remaining history is still linearizable. And vice versa, if the smaller history is linearizable, you add back the operations on that value, the entire history is also linearizable. So our job becomes easier, right? If given a history, we can just repetitively remove linearizability-preserving values until it cannot be removed anymore. And if the remaining history is still non-empty, and then we can conclude that the history is not linearizable. Yeah, and we can actually improve the efficiency a little bit, and we can short-circuit this and say that, okay, if halfway through we find out that the history must not be linearizable, then we can just return bottom as the linearizability-preserving value. So yeah, the main result is that linearizability monitoring is polynomial time reducible to finding linearizability-preserving values. And as a treat, I'll show you how you can find linearizability-preserving value for stack. So for queues and priority queues, it's presented in the paper, and for more information, you can refer to it. But today, I can show you how you can find it for stack. So for stack, there's this thing called the potentially bottom value. So potentially bottom value is a value that is potentially at the bottom of the stack for some legal linearization for the history. And we have to show 2 things. One thing is that potentially bottom value is indeed a linearization preserving value. And second thing is that if there's no potentially bottom value, then the history is not linearizable. Then as such, you can return bottom as the linearizability preserving value. So the first thing, but potentially bottom value is a linearizability preserving value. First, you can see that from the diagram, if you remove the operations for the value 1, the remaining blue instance is still going to be linearizable if the whole history is linearizable. And conversely, if the remaining history is linearizable, we can just squeeze the linearization into the gray part away from the red region. And then we can just put back the operations for push 1 and pop 1. And this is still going to be a legal linearization for the entire history. And the second point is that if a history is linearizable, then a potentially bottom value must exist. Why? Because you can just take any legal linearization and say, hey, the first value that is being pushed in is the potentially bottom value. So our approach for finding linearizability preserving value for stack can be naively implemented in ON square. And that means for the general linearizability monitoring problem, it can be done in N-cube. And actually, this can be further improved into n log n if we use some other data structures to analyze the algorithm. And for example, segment trees, we use segment trees and interval trees to improve the time complexity to n log n. Yeah, for more information, you can refer to the paper. Yeah, so we implemented our algorithms and run it in WSL Ubuntu and test it against existing tools. Our tool is shown that our tool is much faster for stack traces and for queue traces as well. And we also stress test our tool against history of up to 1 million operations, and it can be shown that it runs in less than a second. Yeah. So with that, I've come to the end of the presentation.